polynomials. So this will be, I guess, the soft talk of this workshop, and I will just talk about the enumeration of minimal dominating sets, or in general the enumeration of objects. And in this talk it will be about minimal dominating sets, and at the end on some variants of the minimal dominating sets. So I will just define what is an enumeration problem, and talk about a bit for the generation what is a minimal dominating set. If everybody here knows what are dominating sets, its relation to the transversal hypergraph problem, what kind of reductions we can define for the minimal dominating set to reduce to other graph classes with same problem, and get new polynomial algorithms, and finish by some open problems on this. So what is an enumeration problem? Is just you give a structure, say a graph, you have a graph G and a predicate on this graph G, and what you want is to enumerate the subsets of the domain of your structure, the subset of vertices of your graph that verifies some property, the property P. For instance, you want to enumerate the set of maximal clicks, or the set of maximal independent sets, or a basis of a matrix, etc. So these are interesting because in many areas we are not just interested in checking if a property is verified. For instance, in data mining or in databases, you are not only interested in checking a property, but enumerating all the sets or all the objects that verify that property. So for some of these problems there are some enumeration. So enumeration, the set of objects we want to enumerate is most of the time very large compared to the size of the structure in input. So we cannot define a notion of polynomial time by saying that our algorithm will finish in time polynomial to the size of A, because we want to enumerate a set which size is greater than the size of A in general. So we need to redefine what we mean by polynomial algorithm for an enumeration algorithm. Well, we'll say that our algorithm is an output polynomial if at the end of the algorithm the time is a polynomial that depends on the size of our structure, here of our graph for instance, and the size of the outputs. So for instance, if you take the maximal clicks, then we say that you have a polynomial, an output polynomial time algorithm for enumerating the maximal clicks. If you have an algorithm that enumerates the given a graph, outputs all the maximal clicks of the graph in time polynomial in the size of the set of maximal clicks. And we say that your output polynomial, or your polynomial algorithm, is polynomial delay, or if the delay between two consecutive outputs is also a polynomial. Then if you have a polynomial delay algorithm for an enumeration algorithm, then this algorithm is also an output polynomial algorithm, since you will have the polynomial, which is the delay, times the size of the set of the output set. Of course, output polynomial does not imply polynomial delay algorithm. And for the space complexity, it just depends on the size of the structure and the size. You will say that it is polynomial if it depends on the size of the structure. Oops. For instance, the maximal clicks, there exists a polynomial delay algorithm to enumerate the set of maximal clicks, the sets of bases of a matrix, etc., and many other examples. So, in this talk we are interested in enumerating the set of minimal dominating sets. So I recall what is a dominating set. It is in a dominating set in a graph G is a subset of the vertex of G, such that it hits each neighborhood of each vertex. So this is just an example. If you take x1, x5 and x3, it is a dominating set of our graph G. It is minimal if it does not contain if our dominating set does not contain no dominating set has a subset. For instance, x5, x1, x3 is not a minimal dominating set, but x1, x5 is a minimal dominating set with respect to just the set inclusion. And the problem we want to enumerate, given a graph G, the set of a minimal dominating sets of this graph. This is a well-studied, computing the minimum dominating set is a well-studied problem, but this problem of enumerating the set of minimal dominating sets is not a well-studied problem compared to other enumeration problems like the maximal cliques and the independent sets and so on. But for instance, for this graph, you have many minimal dominating sets. Because they are not the alone, there are many other minimal dominating sets here. So, the minimal dominating sets are related to a problem in hypergraphs. What is a hypergraph? It's just a set and a subset of the power set of the vertex set. The hypergraph generalized graph because if you have a graph, each edge is of size 2, and then you can say that your graph is just the vertex set and a subset of vertices and a subset of pairs of vertices. And the transversal is just a heating set of the set of hyper edges of your hypergraph. So for instance, if you have this hypergraph, the red vertices hits every other hyper edge, then it is a transversal of your hypergraph. Then the problem of enumeration of transversals that I will call the transhype problem. This problem is a well-known problem in hypergraph theory because it is related, for instance, to the dualization of monotone Boolean function. And also it is well studied in data mining problems and in databases. Well, how this problem is related to the dominating sets? If you take a graph G and you take the neighborhood hypergraph of G, that means you take the vertex sets as a vertex set of your hypergraph, and has hyper edges, you take the closed neighborhood of each vertex. The closed neighborhood is a set of neighbors of X including X. Then what you have is that the minimal dominating set of your graph is the set of minimal transversals of the neighborhood hypergraphs. Well, not all hypergraphs are neighborhood hypergraphs of graphs. So there are some hypergraphs that are not neighborhood graphs, hypergraphs of G. So that means that if you want to enumerate the set of minimal dominating sets of a graph, and if you have an algorithm to enumerate the transversals of a hypergraph, then you have an algorithm to enumerate the minimal dominating sets of your graph. Unfortunately, we do not have actually polynomial time algorithm to enumerate the set of transversals of a hypergraph. What we have is just a quasi-polynomial algorithm. So, transhype is a well-studied problem. The best algorithm which is known is this quasi-polynomial algorithm by Feldman and Pascal from about 20 years, if I do not make mistakes. But actually, there are many hypergraph classes where people looked for these transversal problems and have proved that these transversal problems has a polynomial output or a polynomial delay algorithm. It's the case, for instance, for hypergraphs of bounded trivets or hypergraphs of bounded hypertrivets, etc. And then from these examples of hypergraphs of bounded widths where we can enumerate the set of transversals in polynomial delay or with an out polynomial delay, we can say some example of graphs where the problem is output polynomial or polynomial. For instance, if your graph is strongly chordal, which includes indirect epoch graphs or interval graphs, the chordal comparability graphs, etc., then you can enumerate in polynomial delay, in linear delay even, the set of minimal dominating sets. Because in fact, if you are strongly chordal, then you are beta acyclic hypergraphs, and this hypergraph you can enumerate the set of minimal transversals. It's the case, for instance, if your graph is degenerate. Gottlob and others have defined a notion of degeneracy for hypergraphs that generalizes the notion of trivets, the notion of degeneracy in graphs. And then if your graph is degenerate, the neighborhood hypergraph is degenerate, and then you can have also a polynomial delay algorithm. I can just notice that for graphs of bounded widths, you can enumerate in constant delay the set of minimal dominating sets due to a result by Purcell and also Bagan, which shows that every MSN1 problem you can enumerate the set of satisfiable sets in constant delay. That means that the delay between two outputs depends only on the size of the outputs, next output. Well, this is an example of a set of a class of graphs where we can have a polynomial delay algorithms without using any of these results. This is a new result which is not so difficult to obtain, and it does not use any of these reductions from hypergraph or from click, because split graphs do not have bounded click weights, and the neighborhood hypergraph or split decomposition does not fit in any of the, to our best known, of any of these classes of hypergraphs where the transversal problem is known to be output polynomial. Well, we have some classes of graphs where we know an enumeration algorithm in polynomial time. We know from what is from here that it seems that enumerating the minimal dominating set of a graph is perhaps easier than the enumeration of the transversal of the transversals in hypergraphs. So we can perhaps expect to have a polynomial time algorithm for the enumeration of the minimal dominating sets, but actually it's not the case unless we have one for enumeration of the transversal problem. We do not have an algorithm, a polynomial or an output polynomial algorithm to enumerate the minimal dominating sets. I will show you the reduction from transversal problem to the hypergraph, to the enumeration of minimal dominating sets. First, I will not give the proof of this, that you cannot have a one-to-one reduction from transversal hypergraph to enumeration of minimal dominating sets. That means you do not have a reduction that given a hypergraphs, construct a graph such that the transversal of the hypergraphs are exactly the dominant exactly the minimal dominating sets of the graph you have constructed. But you can construct a graph from any hypergraph such that the minimal dominating sets of the graph you will construct is the set of minimal transversals of your hypergraph plus some bounded number of minimal transversal, or polynomial number of minimal dominating sets. How to do that? So this is what is called the incidence graph of a hypergraph H. That means here you have the hyper H's. here you have the vertices of your hypergraph, and you put an edge between a vertex and the vertex representing a hyperedge if the vertex is in the hyperedge. Then from this incidence hypergraph, you can construct a split graph where you just complete the set of vertices into a clique. From this one, you complete this upper set also into a clique, and you add this new vertex V, which will be connected to all the vertices. Then this graph B of H is a co-bipartite graph, and this co-bipartite graph has a property that the dominating sets, the minimal dominating sets of this bipartite graph is exactly the minimal transversal of your hypergraph, and a polynomial number of minimal dominating sets. Then this polynomial number of minimal dominating sets has either at most n square, and they are of this form x, a vertex here and a vertex here. They are of this form. And then if you have an output polynomial algorithm to enumerate the minimal dominating sets in graphs or even in co-bipartite graphs, then you can enumerate the transversals of any hypergraph. But this reductions is not a polynomial, is not a constant delay to a constant delay. It's a polynomial delay to another polynomial delay, because this set is actually at most n square. Now, so we know from this that we cannot expect, unless we have a polynomial delay algorithm or an output polynomial delay algorithm for transcribe for minimal dominating sets. So we must search, as it is done in the case of hypergraphs, then for graph classes where you can where you can solve the enumeration of minimal dominating sets. More classes than the already known classes of graphs. Then a technique is that we borrow from kernelizations or NP complete problem is a notion that we have called the completion. The goal is just, if I have a graph, I want to transform the graph if I have a class of graph C, I wanted to transform it into a class of graph C prime, such that I know how to enumerate the set of minimal dominating sets in the class C prime, and then I have a reduction from C to C prime and get algorithm for this class of graphs. And a way to do that is, for instance, by adding some edges or by deleting edges, vertices, and so on. This example will show that with the completion we add some vertices, some edges, and then transform a class of graphs into another class of graphs. So, what is a completion? So I will say that a vertex is irredundant if it is contained in another, if it does not contain the neighborhood of another vertex. What does it mean? That means just if I have x, I have y. This is the neighborhood of x. Then if the neighborhood of y is included in the neighborhood of x, then x is not redundant. It is not irredundant. It is redundant. Then if I take the set of redundant vertices and I add new edges between this set of redundant vertices, then I have a new graph. And what you get, this is for instance an example. Donc this set, the black ones are the irredundant vertices and the white are the redundant vertices. After completion, we add these edges and we have a clique between the redundant vertices. And then the property is that after doing this operation, you do not modify the set of minimal dominating sets. The set of minimal dominating set is the same. And some other properties, for instance, but if your completion is chordal, it is actually a split graph. It is exactly a split graph, if only if it is a chordal graph. For instance, the results on split graphs, you can extend it to P6 free chordal graphs. Because for the P6 free chordal graph, by doing this completion, you can get a split graph. And then you can reduce your graph to another graph. Now, other type of reductions that in this case you want to remove vertices or edges, then I will say that two vertices are equivalent with respect to this operation if I take the set of irredundant vertices. If I take X, the neighborhood of X, and I take its intersection with the set of irredundant vertices, then it's the same with if I look X or Y. Some property says that there are two equivalent if you can obtain if you can obtain the minimal dominating of set containing X from the minimal dominating set containing Y. That you can, if you look at the minimal dominating set not containing X, then it is actually the minimal dominating sets where you remove X. And if you remove each class of this equivalence class, in each class we remove all the redundant vertices. It is redundant here, then you can compute the minimal dominating sets by using these two properties. From the minimal dominating set of the new graph, you compute. To finish, so there are some other problems that we have looked where we know that it is either NP complete or some other variants of minimal dominating set, like the total dominating set, where we have proved that the enumeration is actually equivalent to the enumeration of the transversal hypergraph. And then this problem is polynomially equivalent, for instance, to the enumeration of minimal dominating sets. And for the collective dominating set, for instance, it is at least has a transhype. It is actually, in some graph classes, it is has a transhype problem, and in some graph classes, it is less hard than the transhype problem. So some new directions just to identify new graph classes where the domination problem is output polynomial. Unless or find an output polynomial for all graphs and look at further at these reductions or this notion of completions. And for instance, get a reduction equivalent to the characterization saying that chordal is equivalent to split in other graph classes. Thank you.